Let's look at a PVA example. A ball is thrown vertically upward from the edge of a building, and it eventually hits the ground next to the building. If the height of the ball is at any given time is h of t is equal to negative 16t squared plus 64t plus 80, and we're going to answer the following. Number one, sketch a diagram and label values at important places. So here we have h of 0. This will be the height at time equals 0. This is where the ball is gonna start up being, and then it gets thrown up into the air, and eventually the ball will hit its peak, and that is when velocity is going to be equal to 0, and then it's going to start falling, and eventually it's going to hit the ground. And when it hits the ground, that's when the height h of t will be equal to 0. Okay. We're going to be involving velocity and acceleration throughout the problems on this worksheet. So I'm going to just go ahead and find the derivatives. Here we have h of t. Here's the position function. And if I want to find the velocity function, I can simply find the derivative. So go through power rule. Negative 16t squared becomes negative 32t. 64t becomes 64. 80 is a constant, so that's going to go to 0. Okay. And when we're at the velocity function, we can find the derivative to get to the acceleration function. So negative 32t becomes negative 32. 64 is a constant, so that's going to drop out. And a of acceleration is simply going to be negative 32 feet per second squared due to force of gravity. And let's look at number 2. How tall is the building? So the height of the building is going to be h of 0. At time 0, we can find out the position of the ball. And if we plug 0 into the position function, we get 0 plus 0 plus 80, so 80 feet. Okay. Number 3, when does the ball reach maximum height? We know the ball will reach maximum height when velocity is equal to 0. So we can simply find t when v of t is equal to 0. So we're going to take our velocity function, set it equal to 0, and solve for time, because number 3 is asking for time, it's asking for when. So we take our velocity function, set that equal to 0, and then we just solve for t. So subtract 64 from both sides, or I can add 32 to both sides, 32t to both sides, and then divide both sides by 32. I get t is equal to 2 seconds. So at 2 seconds will be when the ball reaches its peak, when the velocity becomes 0. Okay, so number 4, what is the maximum height? We know the maximum height will occur when the velocity is 0. We know velocity will be 0 at 2 seconds. That's what we found from number 3. So we can simply plug 2 seconds into the position function, and then in return we can find out the exact location or the exact height of that ball. So we plug 2 into the position function. So negative 16 times 2 squared plus 64 times 2 plus 80, and that'll get us to 144 feet. Okay, number 5, how long does it take to hit the ground? Well, we know that we can find out when the ball hits the ground by setting the position function equal to 0, right? Initially, the height is at 80, but we want to figure out how long does it take for the ball to reach a height of 0, or to reach a location of 0. So if we set our position function equal to 0, and if we solve for t, then we can figure out how long it takes for the ball to hit the ground. Okay, and ground will be where h of t is 0, where the position or the height is 0. So we set h of t equal to 0. Here we have negative 16t squared plus 64t plus 80. We can factor out a negative 16, and that'll leave us with t squared minus 4t minus 5. And once we have that, we can factor this to be t minus 5 times t plus 1. We solve for t, we get 5 seconds and negative 1 seconds. However, negative 1 is not going to make sense for our problem, since t is greater than or equal to 0, based off of this following. So we're only going to keep t is equal to 5 seconds. But graphically, -1 does make sense because if you have a parabola, this parabola is eventually going to come down and hit the x-intercept at -1. But for this problem, since we're starting here, moving to the right, anything to the left of 0 is not going to make sense for our problem. Okay, so we know it takes 5 seconds to for the ball to hit the ground. What's the initial velocity? So initial velocity is going to be find the velocity when time is equal to 0. That's what initial velocity is. So we plug 0 into velocity function. So -32t plus 64, -32 is times 0 plus 64, which is 64, and it should be 64 feet per second. Right. Number 7, what's the velocity at 1 second, at 2 seconds? So we simply plug 1 and 2 into the velocity function separately. And v of 1, we get 32 feet per second. V of 2, we get 0 feet per second. So this makes sense. We see the velocity. Once it gets thrown up, then thrown up into the air, we see the velocity is starting to decrease until at time t equals 0, when it hits its maximum height and the velocity reaches 0. What is the height at 3 seconds? So 3 seconds, we plug 3 into the position function, and we enter all that in. Totaled all that up, we get 128 feet. Okay, number 9, what is the speed when it hits the ground? So speed is very much related to velocity. So if we find the velocity when it hits the ground, then we can use that to find speed. So we know that the ball will hit the ground at 5 seconds. We found that from previous portion, number 5. How long does it take to hit the ground? We found when we set the position equal to 0, we found that it took 5 seconds for the ball to hit the ground. So we can simply plug 5 into the velocity function to find out how fast the ball is going right when it hits the ground. And if we plug 5 into the velocity function, we replace t with 5, and we total that up to be -96 feet per second. However, it's asking for speed, so speed is simply the absolute value of velocity. So -96 feet per second is the velocity, but the speed will just simply be 96 feet per second. What's the acceleration? At 1 second, at 2 seconds, the acceleration due to gravity will be a constant. So no matter whether it's 1 second or 2 seconds, it'll remain at -32 feet per second squared. Okay, here are some additional ones for us to look at. So for number 11, the question here is asking, find the average velocity between 0 and 2 seconds. Now here's a source of confusion for students. Finding the average velocity is not the same thing as finding the velocity at a specific moment in time. So if we want to find a specific velocity at a very specific time, we're going to be using the derivative function, because we want to find the exact velocity, the exact slope of the tangent line to the curve. However, the average velocity is the change in distance, or the change in height over the change in time over these two endpoints. So average velocity will always give you two endpoints to allow you to find the slope. And this simply requires us to use algebra. There's no calculus involved. So that's the big difference here. With instantaneous velocity, we're using the derivative function. For average velocity, we're simply taking the change in position over the change in time, or the change in height over the change in time. So we plug 0 into the position function, we're going to get 80. Plug 2 into the position function, we'll get 144. And so we simply find the slope between the two endpoints. So between 0, 80, and 2, 144, change in height over change in time, So 144 minus 80 over 2 minus 0, which is 32 feet per second. Okay, now it just so happens that the average velocity between 0 and 2 seconds is the same as the average velocity at 1 second, but that's not always going to be the case. We're just going to have to make sure we go through the correct procedure. If they're asking for average velocity, use slope formula. Okay, and if they're asking for instantaneous velocity at a specific point, then many times you're going to be requiring to use derivative unless you have a straight line. Then the slope will be constant all the way throughout. Okay. Okay. Now, if the average velocity is the change in position over the change in time, then it should make sense that the average acceleration is the change in velocity over the change in time. Okay. Again, average acceleration is not the same as the instantaneous acceleration. So we need to take the endpoints, plug them into the velocity function, and find the order pairs for velocity. So v of 2 gives us 0, and v of 1 gives us 32. So we do 0 minus 32 over 2 minus 1, which is negative 32 over 1, which is negative 32 feet per second squared. Now the only acceleration that is occurring is due to gravity, and because the acceleration is constant, and so basically this acceleration is going to be a straight line, a constant slope. So that is why in this case the average acceleration is also the same value. But usually you're not going to be getting the same value between instantaneous acceleration and average acceleration, especially if we're dealing with a more complex problem. Okay, but just keep in mind the steps that you're going to take for average acceleration versus the step you're going to be taking with the derivative when they're asking for the instantaneous acceleration. Okay, 13 is the speed increasing or decreasing at t equals 1 second. So with the previous page, we talked about how we can find increasing or decreasing speed by comparing the velocity and acceleration and their signs. If acceleration and velocity have the same signs, either plus plus or negative negative, then we know there's going to be increasing speed. Decreasing speed occurs when velocity and acceleration have opposite signs, either positive negative or negative positive. Okay, and if we find, so we can compare v of 1 we found from before, velocity at 1 second is 32 feet per second. The acceleration at 1 second is negative 32 feet per second squared. Okay, and so we see velocity is positive, acceleration is negative. They have opposite signs. Therefore, we know at t equals 1, the speed will be decreasing at that moment.